Welcome back to another in our series. Today we'll be looking at circuit analysis using the resistance equation. Now, there are many instances where we are asked to find the total resistance of a circuit. And what's the purpose of really finding that resistance? The fact is, finding resistance is really a means to an end. So if we use the resistance equation, it must have some useful purpose. In order to determine the voltage or power or energy associated with any resistor in a network, it requires information about the current flowing through that resistor. This current must, however, be first determined by finding the total resistance of the circuit or the resistance at different points or sections in the circuit. Now, the resistance equation, as we have shown in one of our videos, is one method of finding the circuit resistance. However, how useful is it in finding the currents flowing through the circuit? Now, let's consider this network where we have 5 resistors, and the resistance equation, as shown, will be developed. For this equation, we'll have R1 in series with the rest of the circuit. The rest of the circuit consists of R2, which is in series with the rest of the circuit. And then R3, which is in parallel with the rest of the circuit. And the rest of the circuit consists of R4 and R5, which are in series. Now that's just a very brief recap of resistance equation. So using this equation and substituting the numbers for R1, we have 3, R2 11, 9 for R3, 14 for R4, and 4 for R5. If we substituted these, then we'll have the 4 and 14 in series to give us 18. We'll have 9 and 18 in parallel to give us 6. We'll have 6 plus 11 to give us 17. And we have 17 plus 3 to give us 20, thereby giving us a total resistance of 20 ohms. Now, let's test the usefulness of using this resistance equation. Here I have the same circuit. This is the resistance equation, and we are going to make Vs 120 volts. How do we use that in finding the currents in all these resistors? Let's get started. So just by looking at the equation, we already know that the total resistance is 20 ohms. For a voltage of 120 volts, we know that I, which would be the current from the source, would be equal to 120 over 20, which gives us 6 amperes. Now let's look at our equation. From our equation, we see that the 3 ohm resistor is in series with the rest of the circuit. So it means that the current through the 3 ohm, which was I1, would be equal to IT, which is equal to 6 amperes. Next, the next resistor we see is the 11, which is within the rest of the circuit. And that resistor being in series with I1, or with the 3 ohm resistor, based on the plus sign that we have here, is telling us that I1 would be equal to I2, which is equal to 6 amperes. So the current through the 11 ohm resistor is equal to 6 amperes. Now let's go to the rest of the circuit. It tells us that these 6 amperes, so 6 amperes would be here, 6 amperes would be here, but 6 amperes goes to the rest of the circuit. And what does the rest of the circuit consist of? It consists of the 9 ohm in parallel with the 14 in series with the 6. But let's look back at the resistance equation that we found. And we saw that that 9 ohm resistor in parallel with the 14 and the 4, it gave us an equivalent resistance of 6 ohms. So what we know is that all 6 amperes will be flowing into an equivalent, I'm going to call it R equivalent, of 6 ohms. Which means that the voltage across that branch, would be equal to 6 times 6, which is equal to 36 volts. So now we know that there are 36 volts across these parallel sections. And what do we know about parallel circuits? The voltage will be the same. So from our equation, we know that we have a 9 ohm resistance. So the current through the 9 ohm, which is I3, would be equal to the voltage across it. This should be 36. Be equal to the voltage across it, which would be 36 divided by 9, which gives us 4 amperes. But because we already know that 9 was in parallel with the rest of the circuit, we can look back at our equation and see that the 9 was in parallel with 18 ohms. So the current in the 18 ohm section, which is I4, would be equal to 36 divided by 18, which is 2 amperes. So I now know that 2 amperes will be going to the rest of the circuit. And what does the rest of the circuit consist of? A 14 ohm resistor in series with a 4 ohm resistor. So it means therefore that the same current would be passing through both resistances. So I4 would be equal to I5, which is equal to 2 amperes. So we have I1, and I didn't really need to look back at the circuit, I'm just using the equation. I1, 6 amperes. I2, which is equal to I1, 6 amperes. I3, which is the current through the 9 ohm resistor, 4 amperes. I4, current through the 14 ohm resistor, 2 amperes. I5, current through the 4 ohm resistor, also 2 amperes. So now I have the current through all my resistors just by looking at the resistance equation. So in summary, we would have to develop our equation. So we develop our equation. Secondly, we will determine the resistance at each point. And then lastly, we will determine the branch currents based on series, which is represented by the plus sign, or parallel, represented by our arrows from the equation. And that is how we use the resistance equation for circuit analysis. And thank you for your attention.